energy. Now, what is the definition of this? The gravitational potential energy at a point in a gravitational field is defined as the work done in bringing or to bring a given body from infinity to that point without acceleration. So if you look at the definition of this, the gravitational potential energy, and the previous one, the gravitational potential, you may say that they look almost alike. They sound almost alike. But actually there is a small difference in the definition if you look carefully. Okay, let's have a look at that definition once again. So this definition, it says here that gravitational potential at a point is defined as the work done in bringing a unit mass. So this is where the difference lies. Okay, but here it is to bring a given body. So the body here is not of unit mass. Okay, so similarly here, to find the gravitational potential, the expression for the gravitational potential energy, what we need to do is we only have to find the work done to bring that body from infinity to that point. All right, so the procedure is basically very similar. Okay, so let us consider this diagram once again. So in this diagram, mind you that now m is not equal to 1, a small mass at a which is at a distance x from the earth. All right, so basically if the small mass is here and the earth is here, then what will be the gravitational force between the two? The gravitational force between the two is F is equal to G, mass of the earth, mass of the body, by distance. What is the distance? Distance is x, distance square. Let's call that sum equation 1. Okay, then what we need to do, we need to find the work done to bring from infinity to point P. To do that, we first have to find the small work done, dW. All right, so what is that small work done? Small work done to bring or to bring the mass from A to B is what is dW. This is F dx. Why dx? Because we are taking from A to B and that small displacement is dx. So put the value of F from there, G m by x square dx. So that is equation 2. Okay, so what is this dW? It is just the work done to take the body from A to B. Now if you want to find the total work done, we just integrate this. So therefore total work done to bring the body from infinity to P is what is W, which is equal to integration of dW. Integration of dW is G m by x squared dx. And what is the limit of integration? Again, where from you're taking the body from infinity, is it not? So when this small mass is at infinity, its distance, that means x, would be infinite. When you take it to point P, its distance from the earth would be r. So here the limit of integration is the same. It will be from infinity to small r. Okay, mind you, not capital R, because you're not taking it to the surface. All right, you're not taking it to the surface. If you take it to the surface, then it would have been capital R, but you're taking it to point P. So here again we perform this integration and we find that this integration is minus G m by r yes. So let's call this sum equation 3. But this work done is equal to the gravitational potential energy at P. So therefore the gravitational potential energy This is often denoted by U. This will be minus gmm by r. Okay, so that is our required expression. Okay, let's call this some equation 4. Right. So again, let us take some important points here. So what are the important points? So this is very similar to the gravitational potential only. So if r increases, as r increase, what happened to u? U also will increases. Okay, so b, if r is infinite, what will be the value of u? U will be 0, which is maximum. So you may ask me, how come u is 0 but then I'm taking to be, I said that it is maximum. How can that be? You see here, if r increase, then what happened to this part? Just forget about the minus sign. If r increase, then this part without taking the minus sign will decrease, is it not? Will decrease. So as r increases, this is decreasing. So now if we consider the minus sign, then it becomes less and less negative. No, less and less negative. So let me just give you, suppose we go from minus 10, and then we go to minus 9, we go to minus 8, and then we go to minus 2, we go to minus 1. Okay, then finally we go to 0. So if we go in this way, isn't it less and less negative? Isn't it less and less negative? But if we go in that way, that means it is increasing. Yes or no? Why? Because minus 9 is larger than minus 10. Minus 8 is larger than minus 9. And so on. Minus 1 is larger than minus 2. So in this way, it is increases. So that's why as r increase, u also will increase. You got it? So it becomes less and less negative. Okay. So at the most, it can be 0. All right. So that is when it is maximum. So that is the reason. Okay, so that is the, enough. So those are the important points in this discussion. Okay, now what about, let's say we want to find the gravitational potential energy of a body at a small height. Okay, let me write down that heading. Okay, so in this figure, let's say we have this body on the ground, and on the ground the surface, what is the expression for gravitational potential energy? U1, this is minus g m by, what is the distance now? Distance now will be r, is it not? Since the value of small r now will be equal to capital R. Okay, now at a small height h, u2 will be 1 minus gmm. What is the distance of the body now? It will be r plus h. Okay, let's call this some equation 2, and this is equation 1. So therefore, what is the change in potential energy? Delta U. Delta U will be, tell me first which one is higher, U1 or U2? We have said that as you go further and further away from the Earth's surface, the potential energy increases. So therefore, U2 will be larger. So here it will be U2 minus U1. So minus gmm r plus h minus of minus gm by r. So this becomes, this will be plus, right? So I take common gm, then inside bracket gmm, sorry, inside bracket I will have 1 by r, minus 1 by r plus h. Okay, so delta U, this will be how much? GMM. Then I can perform the LCM out here. LCM will be r times r plus h, right? So this divided by r, you get only this, so you have r plus h minus r. Okay, so this r and this r will go, so you have GMM r square plus, okay, I can do one thing. Instead of multiplying r square, let me write it as r plus h only. All right, and didn't we say that this height is very small? Since h is very small compared to capital R, then isn't r plus h nearly equal to r itself? So therefore this difference in potential energy will be G r by r square. That is h here. That is h. Okay, so here also I should be getting h. Okay, so you have m g h, since g is equal to gm by r square. All right, so this is delta u. Okay, now usually what we take is on the surface. Usually on the surface, the potential energy, we take it to be 0. Okay, so that means u1 is 0, and the potential energy on some height, we take it to be u. So therefore here you have u, this delta u is what? Isn't this u2 minus u1? So instead of u2 I will write u, instead of u1 I will write 0 is equal to mgh. So you have u is equal to mgh. This is the expression for the gravitational potential energy. Okay, which is very clear that as h increases, gravitational potential energy also increases. Thank you.